Hey everyone, and welcome to today's Explainer. We're jumping right into a really fun one today, the physics of period and frequency. Basically, we're going to demystify the foundational physics of how the universe repeats itself. From the beating of your own heart to the invisible signals beaming down from space, our entire world is governed by cycles. And today we'll unpack exactly how engineers and physicists measure, understand, and actually harness those cycles. By the end of this explainer, I promise you're going to look at everything around you, from the ceiling fan in your living room to satellites in orbit, in a totally different way. So let's get into it.
To really ground ourselves here, I want you to imagine something, well, incredibly peaceful. Picture yourself standing barefoot on a sandy beach. You're just looking out at the ocean, right? And a wave washes up, gently reaching your feet. The water recedes, a few moments pass, and then another wave arrives, and then another, and another. You, right there on that beach, are experiencing a repeating event.
Now, as you stand there watching that water roll in, your brain is probably going to start looking for a pattern. It's just human nature. You might find yourself asking a really simple but honestly profoundly important question: how long does it take between these waves? Are we waiting 5 seconds? Maybe 10 seconds? Without even realizing it, you're instinctively trying to calculate the duration of a repeating event.
Okay, let's dive into this, because this is where it gets interesting. On one hand, we've got that first question, how long does one cycle take? But what if we ask a completely different question about that exact same ocean? What if we ask, how many waves arrive each minute? Or how many cycles happen each second? These two questions right here represent two of the most important concepts in all of physics and engineering. They describe the exact same repeating motion, but from two entirely different, yet perfectly connected perspectives.
So that first perspective, that's what we call the period. The period is simply the time required to complete one full, distinct cycle of a repeating event. We use a capital letter T to represent it, and we measure it in seconds. Think about a single swing of a grandfather clock's pendulum, or the time it takes a satellite to complete one full orbit around the Earth. Basically, if you're asking how long does this one specific cycle take to finish, you are asking for the period.
But let's completely flip the script for a second. What if we stop caring about how long one cycle takes, and instead focus on a set amount of time, let's say 1 second, and we just count how many cycles we can cram into it? See, we're no longer looking at duration. We are looking at a rate. How many times does this happen each second?
Now, what's really interesting about this mathematical shift is how beautifully simple it is. This is frequency. Frequency measures exactly how many cycles occur every single second. We use a lowercase f for its symbol, and we measure it in a unit called hertz, named after the famous physicist Heinrich Hertz. And 1 hertz literally just means one cycle happens every second. That's the whole thing. If a clock ticks once a second, its frequency is 1 hertz. If the electricity in your wall plug changes direction 50 times every second, it has a frequency of 50 hertz.
To put that into perspective, let's look at how beautifully these concepts mirror each other in everyday life. Take a pendulum. A 2-second period means a frequency of 0.5 hertz, so half a swing per second. Or a ceiling fan rotating 60 times a second. That's a frequency of 60 hertz, making its period a tiny fraction of a second, about 0.017 seconds. And finally, a resting heartbeat with 1 beat per second gives us a period of 1 second, and perfectly, a frequency of 1 hertz. You can see their exact mathematical opposites. When the period goes up, the frequency goes down.
But hey, this isn't just about fans and pendulums. This concept governs the entire universe of waves. Literally every single wave has a frequency. We started with ocean waves, which repeat pretty slowly, right? But there are also sound waves traveling to your ears right now. There are light waves hitting your eyes. There are radio waves carrying your favorite music and GPS signals guiding your car. Whether a wave has a low frequency and repeats slowly, or a super high frequency and repeats rapidly, absolutely dictates how that wave behaves and how we can use it.
Speaking of repeating rapidly, just take a look at this number: 1,575,420,000. I mean, wow. This isn't just a random massive number, though. This is the exact number of oscillations or cycles that happen every single second in a GPS L1 signal. That means its frequency is over 1.57 gigahertz. Just try to even wrap your mind around a wave waving over 1 billion times in the time it takes you to say the word one. It's pretty mind-blowing.
And this brilliantly illustrates why understanding frequency is so incredibly powerful. Satellite communication relies entirely on these electromagnetic waves. By operating at this blisteringly fast, enormous frequency, GPS satellites can make unimaginably precise timing and positioning measurements.
Because the cycles are happening so incredibly fast, our receivers here on Earth can measure tiny fractions of a second to figure out exactly how far away the satellite is. And that is what places you perfectly on a digital map.
Now, let's contrast that crazy billion cycle per second frequency with this number, 90. This is the orbital period, in minutes, of the International Space Station. So while those GPS radio waves are vibrating frantically, the giant physical structure of the space station is out there completing one slow, majestic orbit around the Earth every 90 minutes. So if the orbital period is 90 minutes, that translates to an orbital frequency of roughly 16 orbits per day. And mission planners absolutely rely on this period. Because it is highly predictable, they use it to perfectly schedule scientific Earth observations. They use it to calculate precision communication windows with the astronauts on board, and they use it to know precisely when the station will pass over specific ground stations. Honestly, without understanding that 90-minute repeating cycle, managing the space station would be chaotic, if not completely impossible.
But understanding frequency isn't just about scheduling or navigation. Sometimes it is literally about survival. And this brings us to a phenomenon called resonance. See, every physical structure in the world, a bridge, an aircraft wing, a skyscraper, a rocket, has a natural frequency. It has a specific rate at which it just wants to vibrate. If an external force repeatedly pushes on that structure at that exact same frequency, the vibrations don't just happen, they grow larger and larger. Think of pushing a child on a swing at just the right moment to make them go higher. In engineering, resonance during an earthquake or high winds can be absolutely destructive. Let's move to a real-world scenario and see how this builds. Think of it like a mini space thriller. Deep inside a billion-dollar spacecraft, a spinning reaction wheel develops a tiny vibration at 20 Hz. Now, unfortunately, the spacecraft's physical structure happens to share that precise 20 Hz natural frequency. Because they match perfectly, resonance builds. Every single rotation pumps more energy into the structure until the whole spacecraft is violently shaking, blurring the telescope and totally compromising the mission.
So how do we save the mission? Well, this is where brilliant engineers step in. During the design phase, long before the rocket ever makes it to the launch pad, they meticulously analyze all the natural frequencies of the spacecraft's parts. If they spot a potential match, they fix it right then and there. They might add stiffness to modify the structure's natural frequency, or they might program that reaction wheel to operate at a totally different speed so it never lingers at that dangerous 20 Hz. Basically, they intentionally detune the system, making absolutely sure those frequencies never coincide.
So as you can see, this is far from just an academic exercise. This physics is the absolute backbone of our modern world. Engineers use frequency to design everything, from the Wi-Fi router sitting in your living room to complex radar systems, aircraft frames, and heavy-duty electric motors. Whether you're trying to perfectly transmit a radio signal all the way across the solar system, or you're just trying to prevent a suspension bridge from collapsing in the wind, understanding frequency plays a central, absolutely vital role.
So the crucial point to take away is this. Period and frequency are forever linked as reciprocal ways of understanding how our world repeats itself. Period, our capital T, is always asking the question of duration. How long does one cycle take? While frequency, our lowercase f, is always asking the question of quantity. How many cycles happen each second? They really are just two sides of the exact same coin. From the slow, steady ticking of a grandfather clock to the billions of invisible waves hitting your phone every single second, the universe really is just a symphony of repeating motions. Understanding period and frequency has allowed us to map the globe, explore the stars, and build the amazing structures of our modern world. But it leaves me wondering, as we continue to push the boundaries of quantum physics and deep space exploration, if understanding how the world repeats itself built our present, what undiscovered frequency holds the key to our future? Thank you so much for joining me on this explainer today. Keep asking questions, stay curious, and I'll catch you next time.